Okay, students, let's add again some additional example or a question on a principle of mathematical induction in order to understand the concept. So here again, you are given a certain, mathematical statements written in terms of natural numbers. Look, by default, you have to understand that whenever you are asked to prove that a certain mathematical statement is true for using principle of mathematical induction, even though it's not written, you see, a set of natural number is considered. So look here, this sum is equivalent to n over n plus 1, you see. So when you take the sum of the first two terms here, you see, this is equivalent to 2 over 2 plus 1 here, which actually is 2 over 3. So if you take again the sum of the first three terms here, look, 1, 2, 3, here it said that this is equivalent to 3 over 3 plus 1, 3 over 4. Actually it works, guys. When you just take the sum of all these three terms, you will obtain this to be 3 over what? 4. This is true. So as you are performing this, or as you are taking this approach, show that this is equivalent to n over n plus 1. So as usual, according to principle of mathematical induction, what we need to do is we need to apply those three steps. But before you continue, as I told you frequently, what you need to do is you have to assume this to be p of a certain variable. So the variable here is n, the variable involved here is n, so call this to be p of n. So the solution runs like this. Call this to be p of n, okay? 1 over 1 times 2. Look, 1 doesn't mean 1.2, guys. This means 1 times 2. 1 over 2 times 3. 1 over 3 times 4. It continuously moves, you see, up to 1 over n times n plus 1. Call this to be p of n. So if you call the entire expression to be p of n, now p of n is, defined in two ways. One is this one, the left expression, and the other is, the right one. I did this intentionally in order to let you understand, the basic concept. Now look, p of n is this one. P of n is also written, in terms of n over n plus 1. So the first thing that we need to do is we have to assure whether this is true or not for the first natural number. So even though it's not written and is assumed to be 1 here, so let's check the first step. Step 1, check that it is true for n is equal to 1. So put 1 here, student. When you put 1 here, it will be 1 over 1 times 2. So which actually is 1 over 2, okay? 1 over 2. This doesn't mean 1.2, guys. It means 1 times 2. 1 over 2. So what will happen if I put 1 here again? 1 over 1 plus 1 comes, which actually is 1 over 2. You see? Do you think that these two are the same for n is equal to 1? Yes. Because here we obtained 1 over 2, here also 1 over 2. So this statement holds true for, n is equal to 1, where p1 is true. So if this is true, we need to go to the other steps. As I told you, if this fails, we must not go to the next steps. Rather, we stop here and conclude that this statement is false. But so long as this is true, now let's go to step 2. In step 2, as I told you, we do have assumption. You see? Look, for how long are you going to check this one? For instance, if you consider, the first three terms here, you believe me that it will be 3 over 4, that is to say 1 over 2 plus 1 over 6, because 2 times 3 makes 6, plus 1 over 12 makes, students, 3 over 4. You can check, please. It holds true. So look, as you are doing this, you always obtain similar output, but we are unable to prove this just simply substituting set of natural numbers or natural numbers in place of n again and again. Instead, assume it holds true up to a certain natural number k. Assume that it holds true up to a certain natural number k. The question is, will it be true for the next natural number? If it holds true for the next natural number, the statement is true according to the principle of mathematical induction. So look, assume it holds true up to a certain natural number, k, as can be shown. So in place of n, you simply substitute k. So p of k is going to be this one. It's a matter of changing n by k. That's all. Look, change n by k, then this can come. So here, assume that the left expression is equivalent to the right one. Assume it works up to a certain natural number, k. The question is, will it be true again for n is equal to k plus 1? Look, when we say n is equal to k plus 1 is, the next number from what? K in natural numbers order. So look, P of K plus 1 is 1 over 1 times 2, 1 over 2 times 3, as you were having here. So for K, you do have 1 over K into K plus 1. Now, when you come to the K plus 1 term, you see you do have 1 over, in place of K, you need to put K plus 1. Look, K plus 1 is set. And again, you need to put K plus 1 in here in K, then K plus 1 turns to be K plus 2. So look, students, P of K plus 1 is this. See, when you consider this one. How about when you consider this one? Look, P of n is defined again in terms of this one. So P of K plus 1 is a matter of, again, putting K plus 1 in place of K n here. So put K plus 1 here, K plus 1 comes here as it is. But here, K plus 1 turns to be K plus 2. You see, student? See, K plus 1, K plus 1 plus 1. Because it was n plus 1 over n plus 1. Now when you put K plus 1 here, K plus 1 over K plus 1 plus 1. Look, K plus 1 over K plus 1 plus 1, which makes K plus 1 over K plus 2. So, dear students, what we need to do is here, you see, we need to show that this sum is equivalent to this one. If we are able to show that this sum is equivalent to this, we are done. We can say that by the principle of mathematical induction, this holds true. Because if we assume that it holds true up to a certain natural number K, if again holds for the next natural number K plus 1, since the set of natural number is endless, we can say that the statement is true for every natural number. So we need to create a mechanism where we can, you see, show that this is equivalent to K plus 1 over K plus 2. To do that, what we need to do is, you see, just take P of K plus 1, the one written over here. You see, the one written over here, just directly take this one. So as you see, it is stated. Now I just have made this to be written by, you see, a yellow color, because this is, you see, taken in your assumption here, students. Look, this is assumed to be, you see, equivalent to K over K plus 1. So in place of this expression, one can take K over K plus 1, because it has been assumed that this is equivalent to K over K plus 1. So directly have K over K plus 1 in place of this one. Then in addition to this, you see the one written by a white expression follows, and that is plus, directly take that as it is, then 1 over K plus 1, K plus 2 comes. You see, students? Now look, our intention here is to show that this is equivalent to what? The one written here, K plus 1 over K plus 2. If this is so, see, this statement is true for n equals K plus 1. Now let's see how this can be equal. Look, we are having here K plus 1, K plus 1, K plus 2, you see, as its denominators. So we need to take least common multiple of these two, and obviously the least common multiple of these two is K plus 1 times K plus 2. So have that, please, K plus 1, K plus 2, and then divide this K plus 1, K plus 2 by K plus 1. K plus 2 times comes, K plus 2 times K is K times K plus 2. But as you are dividing this by this one, you do have 1 times, and 1 times 1 is 1. So look, guys, here we have K into K plus 2 plus 1, K plus 1, K plus 2. Now, dear students, what will happen here? This is K times K, K squared. K times 2, 2K. So it will be K squared plus 2K plus 1. You see? Now let's factorize this. Think of two numbers where their sum can be number 2 and product number 1. They simply are 1 and itself, right? 1 and 1, because as you are taking the sum of 1 and 1, you do have 2, and the product comes 1. So when you factorize K squared plus 2K plus 1, you do have K plus 1 times K plus 1. You see, binomial square, K plus 1, the whole square can come. Then here in the denominator, you do have K plus 1 times K plus 2. So is there an expression to be cancelled here? Yes. K plus 1 can be cancelled by K plus 1. You see? Since K is different from minus 1, we do have, you see, we do have ability to cancel, you see, K plus 1 by K plus 1, no problem. You see, no problem at all. So we can cancel K plus 1 by K plus 1, then K plus 1 over K plus 2 comes. You see, students? You see, the one we were looking for comes here, students. Look, our intention was, you see, to have this sum to be equivalent to K plus 1 over K plus 2. Here we go. So this shows you that this statement is true. That is to say that P of K plus 1 is a true what statement. Now remember, principle of mathematical induction uses 3 steps. Step 1, step 2, and step 3. In the first step, we will try to check for the first number and we obtain that to be true, because P of 1 is obtained to be true. In the second step, we assume, you see, that the statement is true for up to a certain natural number, what k, and we have assumed that. And in the last step, that is in step 3, we need to show that it holds true for n equals k plus 1. Here we showed, hence P of k plus 1 is true. Thus, by the principle of mathematical induction, you see, because it is a principle that says so, by the principle of mathematical induction, we can say that the statement, the one written over here, you see, is a true statement.